Welcome back, class. So we were learning about the signal properties, and last time we learned about the DC or average value of a signal, RMS value of a signal, how we can calculate the energy of a signal, power of a signal, dB and SNR ratios. Now we are going to put more focus on the Fourier transform, the spectrum of a signal in this lecture. So basically this lecture is a review of the concepts which you have learned in the signal and system about the Fourier transform. So we know that if we have a signal in time domain, okay, if you multiply with exponential power minus a to pi ft, and if you integrate from minus infinity to infinity, so that will give you the Fourier transform of that signal. Okay, so basically Fourier transform pair can be written as like this. Okay, or we can also write this in omega form. Okay, so this is angular frequency, this is the simple linear frequency. Okay, so this is called Fourier transform pair for signal, and because we are integrating from minus infinity to infinity, this is also basically called as the two-sided spectrum. Okay, so when we go to the frequency domain and if we plot the signal frequency domain, so that thing is basically called the spectrum. So if you guys remember, if we have a rectangular signal in time domain, okay, so and if we take its Fourier transform, that is basically give us a sinc function. Okay, so this sinc function is basically the omega f magnitude. This is basically the spectrum of the signal. Spectrum means frequency component of the signal, that what is the characteristics of the signal in the frequency form. That is basically referred as the spectrum of a signal. Okay, and if we want to calculate the inverse Fourier transform, so Fourier transform signal will be multiplied with exponential power j to pi ft. Okay, then we can get the inverse Fourier transform of that signal. So usually we use the inspection method or the partial fraction techniques for the calculation of the inverse Fourier transform instead of like using this integration formula. Okay, so that is our usually approach. The important thing is that which we have to understand that the Fourier transform of a signal will exist if it is satisfying these conditions. Okay, that Fourier transform will exist only and only if the both Dirichlet conditions are satisfied. The first one is our any time interval of finite length. The function is single valued with a finite number of maximum and minimum, and the number of discontinuous if any is finite. Okay, so for example, if we have this signal, okay, so it has a finite number of maximum and finite number of minimum, and if there is any discontinuity, it should be minimum. The second thing is this the original signal should be absolutely integratable, or in other words, like if you remember, if our signal is absolutely integrable, that is means our signal is stable basically. So if your signal is stable, then only if and only if in that condition your Fourier transform will exist. Okay, and also we can actually ensure that by calculating the energy of a signal. Okay, like if the signal has finite energy, okay, so basically this is another form of the absolutely integrable. So our signal will be have a Fourier transform. So in conclusion, we can say that all physical waveforms encountered in engineering practices are Fourier transformable. Okay, so usually all physical waveforms which we typically use in engineering applications, they have Fourier transform. Okay, we will see the many examples. Okay, so basically here in this course our focus is not basically using the integration techniques for the calculation of the Fourier transform. We will putting more focus on the using of the properties. Of course, we will start with a simple example. We will see this in live session just to get a review that how we can actually calculate the Fourier transform and its spectrum or spectral components. The properties of the Fourier transform are similar, spectral symmetry of a real signal. Like if the signal are complex conjugate, then their spectrum will have also the symmetry. For example, like for the if you talk about the rectangular signal, okay, so it have a symmetry. Okay, so the positive side and negative side are same. So if similarly, if you look at the spectrum of this signal, the Fourier transform of this signal, so the sinc signal, so the positive side and the negative side basically have symmetry here. Okay, for this case. The next important thing is the calculation of the power and energy. Okay, so we know that if we want to calculate the energy of a signal in time domain, so we take the magnitude square and then we integrate from minus infinity to infinity, and we can calculate the energy of a signal. So Parseval's theorem depict that. Okay, instead of calculating in time domain, okay, if you have the spectrum of a signal, okay, so take the magnitude square of that spectrum and then integrate from minus infinity to infinity, so that will also give us the energy. So basically energy calculated in frequency domain or in time domain, it will be same. So that is basically the Parseval's theorem, that energy is conserved in both domain. Energy is same in both domain. Either you calculate in time domain or in frequency domain, you will get the same value of the energy. So basically, what if we talk about the energy, and if we want to calculate the spectral density of energy, okay, we call this energy spectral density, ESD. So energy spectral density is basically energy density. Whenever we have density, it's per unit of something. So energy density, energy per unit frequency. What is my energy per unit frequency? Okay, so for example, we know that using the Parseval theorem, so we can actually write the energy like this one. Okay, from minus infinity to infinity. Okay, or what we can say that, so basically like if the total frequency is f, okay, so basically whatever we are getting here, so basically that is actually your energy spectral density. Okay, and this is your total frequency. So ratio of the uh, magnitude square of signal, okay, with respect to frequency, okay, that is actually called as energy spectral density, and usually it represents like this one. Okay, or in other words, this is coming here and you are integrating from like if you integrate from minus infinity to infinity, that will give you the total energy of a signal. Okay, so the total energy of the signal is basically the energy density divided by the frequency. So if you multiply the energy spectral density, okay, energy and the frequency, okay, so we can get the actual energy of the signal. Okay, so total normalized energy, so basically the area under the energy spectral density. Okay, or if this is our energy spectral density, we just integrate from minus infinity to infinity or over the complete frequency range, we will get the actual energy of the complete system. Properties of the Fourier transform: linearity, time delay, okay, differentiation, integration. So these are all the properties. Okay, the convolution in time domain is basically the multiplication in frequency domain. If we are having the scaling in time domain, this is basically the frequency, like we replace the f factor with that in frequency domain with that multiplication here. So these are all the properties which we have learned in last time, so we will use them to solve the examples. Okay, so the properties table could be given and you can use them to get the solution of the different problems. Example, we will say this in this example in live session. A review of the impulse. Okay, impulse is a very important signal, okay, in the communication systems. So it's also called as direct delta function. This is another name of the impulse. So the basic property of the impulse is, when a impulse is basically multiply with any signal, we will get this signal value at the impulse location. So this impulse is actually existing as x equal to 0. So we will get the signal value, function value at the impulse location with that impulse. And if you are integrating that thing, so we know that integration of the impulse is 1. So we will get the only function value. So that is the basic first property of the impulse. Very important property. Okay. So whenever a function multiply with an impulse, so this impulse is basically existing at x naught. Okay, shifted impulse. So we will get the function value at the impulse location. Okay, and rest we will get the just impulse, shifted impulse. So shifted impulse or normal impulse, its integration is always 1. Okay, so this is the very important basic property of the impulse. Unit step function, we know that this is a signal which is existing only at the positive interval, and if you take this is 1, okay, so derivative of unit step will be basically uh, 1 with respect to constant, it will be basically 0, okay. So 0 means there is a signal which is existing at 0 only, which is actually your impulse function. So derivative of unit step is basically an impulse, okay. Or in other words, if you integrate an impulse, so what is your answer? 1. Or in signal system, 1 is basically unit step signal, okay. So these are just the interrelated properties of a unit step. And if we talk about this is a spectrum example, okay, we will say this in the live session. So we learned about the impulse. So basically we can use the impulse for the conversion of a continuous time signal into a frequent discrete time signal. For example, if this is a continuous time signal and if you want to convert this to a discrete time signal, that for example I want to get only these samples value to make this a sequence, what we can do, we can multiply the continuous time signal with an impulse train. So wherever I want to get value, so I can multiply with that impulse. So eventually what will happen, whenever an impulse multiply with a function, we will get the function value at impulse location. So our final results will be only this black. So impulse can be used basically as a sampling function. So if we have an impulse train, okay, we can use them for the baseband sampling of the functions. And if you take its frequency domain, so basically in frequency domain we will also get the impulse train, same impulse train, okay, just with a change in the uh, time, the frequency intervals, okay. So that is the end of this part of the lecture. We will solve the relevant examples in the live session. Thank you very much for your time.